In this video, we'll solve graphical, numerical, and symbolic problems about motion. In particular, we'll look at the relationships and distinctions between distance and speed and position and velocity. These are subtle concepts that are hard to get your mind around. We're going to look at one-dimensional motion. That'll make it easier. Problem 1 says, from a stop at home, a car travels east, on the paper that'll be to the right, along a straight road, speeding up before coasting at a constant speed, then slowing down before turning around and going back west to the left to home in the same kind of way. In other words, speeding up, then coasting, then slowing down until you get to a stop. Part A, graph the car's speed versus time. We'll do these one at a time here. This is part A. We want to graph speed versus time. We're not given units. We could have been given units. What would be natural kind of units? Time could be in minutes or hours, and speed could be in miles per hour or kilometers per hour. There are lots of different units that you could use. So the car is starting from a stop. The speed at time 0 is 0. We would implicitly assume that we're starting at time 0. But then the car speeds up. The speed has to increase. Will it increase in a linear way, a straight line, or be concave up like that, or concave down like this? That's actually not so clear. Let's keep it simple. Let's assume it increases in a linear way. You speed up until you get to a coasting speed, and then your speed is constant. It's a constant speed. So at some point, we can make the graph horizontal. Would it really have a corner like that? Probably not. It might have a slight curve to it. That's more reasonable. But again, let's keep it simple and assume it's a horizontal line right there with a corner in the graph. And then the car is going to slow down before turning around. The instant that it turns around, so to speak, or really it's not going to happen in an instant, but maybe over a few seconds, the car's speed is going to be essentially 0. Or very small. So this graph is going to go down towards 0 and essentially be 0 for a few moments in time before now the car is going to go west and speed up again like this, come to some coasting speed, stay constant for a while, and now it's getting back close to home, and the speed has to go down to 0 again when the car comes to a stop. Okay, so that would be a graph of the car's speed versus time. Part B is to do something related. Graph the car's distance traveled versus time. And when I say distance traveled here, we are trying to distinguish distance versus position. Yes, the car goes back and forth, first away from home to the east, before coming back to home going west. But when we're talking distance traveled, we're essentially ignoring the fact that the car goes back and forth. When we talk about its position, essentially its distance from home, then we do take the back and forth into account. So in doing part B, we're ignoring the back and forth. We're only thinking about the speed and not thinking about direction. This is time. This is distance, not from home, but distance traveled. Okay? So at time 0, the car hasn't gone any distance. The car is speeding up from this time to this time right there. And I drew it so that it's a straight line increase in the speed. In other words, the acceleration is constant. What would that mean about the distance traveled? It will not be a straight line. The speed graph, the values of the speed, tell you the slopes of the distance traveled graph. And so the fact that the speed is 0 at time 0 means the slope at time 0 is 0. Then it's slightly positive, so the slope becomes slightly positive. Then it gets higher and higher to some maximum value in speed, you could say. So the distance traveled slope is going to get higher and higher until it reaches some maximum slope. And then when the car is traveling at a constant speed, the distance traveled graph, I need to redraw it here, maybe about like this instead. The distance traveled graph becomes straight at that point. Now, it's a little hard to see here. I do want it to have a slight curvature here. It is concave up right there, and then it's straight right here until we get to this time, and then it's going to become concave down. The speed is going down towards 0, so the rate at which the distance traveled is increasing, decreases. The graph gets to have a smaller and smaller slope. During this small time interval when the car is turning around, effectively the distance traveled is 0, even though it's moving a tiny bit. And then after that point, the same kind of thing happens when the car travels westward. We're going to get this similar kind of graph. It'll go up like this, concave up, then be straight during this time interval from here to here, and then be concave down until when the car is back home, then the slope here is 0 again. So this would be the distance traveled, going back and forth, not thinking about distance from home, not thinking about position, but instead just purely thinking in terms of how far have I gone, okay? Parts C and D, we think about the back and forth. We think about in part C, the graph's eastward, not speed, but velocity versus time. It's an eastward velocity. That means when it's going to the right, right being eastward, that's a positive velocity. And when it's going to the left, the eastward velocity is actually negative. All right, so if we want to make in part C here a graph of the velocity versus time, we want to allow for the velocity to be negative. The speed ultimately ends up being the absolute value of the velocity, is another way to think of this. When the car is traveling eastward, the graph of the velocity is the same as the graph of the speed. So I just copy this piece of the graph over here, essentially like this. But, and then there's the time interval where it turns around, but when the car goes westward to the left, negative velocity, essentially I need to take this piece of the graph right here and reflect it across the time axis, and I get a graph like this. Okay, so that would be a graph of the velocity versus time. Velocity is taking direction into account. We're saying that eastward is positive, which means westward is negative. When you are traveling to the east, it's a positive velocity. When you're traveling to the west, we count it as a negative velocity. This is worth doing, okay? Again, the speed is the absolute value of the velocity. What about the distance from home, the position versus time? I really should have added the word eastward distance. Thinking of eastward, when you are to east of home, that would be like a positive distance, and when you're to the west of home, that would be a negative distance, though the car doesn't get to the west of home. The car comes back home. It comes back to where it starts. Now we're graphing the distance from home, the eastward distance from home. I'm going to call it position in the graph, position. You could call it an eastward position. I'll just use the word position. I drew it as if it could be positive or negative. I didn't have to do that. Actually, it is going to stay positive the entire time. When the car is traveling to the east, the graph of the position is going to be the same as the graph of the distance traveled. So during this part from here to here, concave up at first, then straight, then concave down, the graph is the same. But now when the car goes back home, this part of the graph is not the same. The position eastward from home has got to go back down to 0. Effectively, I need to take this piece of this graph and not flip it about the time axis, but instead flip it essentially about a horizontal line like this, reflect it across a horizontal line like that, and the graph now is going to look like this. Concave down here, then straight, then at the end, slight concave up as it slows down. Okay? And the interpretation here is that by the time you get to the end there, you are back home, okay? So it's kind of neat to see the relationships between these things. Problem 2 is similar to problem number 1, except we are given a graph instead of having to make a graph. The graph of f of t in the figure below gives the position of a particle at time t, okay? Is this linear motion along a straight line? It certainly could be. Is it an east-west line? Not necessarily. It could be. You could probably most effectively think of this as motion along actually this y-axis that you see here. This is the position. It's not the speed or velocity. And the position can increase or it can decrease, because this graph can be increasing right here or decreasing right here. It's probably helpful to imagine the motion before we try to answer these questions. In these questions, we're trying to list the following quantities in order, smallest to largest, various average and instantaneous velocities. But let's imagine the motion first. So I need to imagine time going by at a steady rate here from 0 to say 6 seconds. 6 seconds, maybe I'll even count the seconds as I go here. And the position I'm going to imagine of the particle is along the y-axis. So it's a little tricky here. This is not the actual path of the object. The object is moving along the y-axis. Let's see how well I can do this here. It's going to go fairly fast at first, then it's going to be slowing down because this graph is concave down. The slope of this graph is getting smaller. At one instant in time, looks like about t equals 4. That's when the object reaches its maximum y value and turns around and comes back the other way. And then because this graph has a slope that gets more and more negative, it actually is speeding up as it moves down. So let's see how well I can do this. Ready? Go. 1001, 1002, 1003, 1004, 1005, 1006. Okay, that was hard to do in a steady way with my pen there. But that's the basic idea of what kind of motion this graph is describing. All right, let's look at these quantities that we want to order from smallest to largest. They are velocities. This is a position graph. They're going to be slopes of certain lines in this graph that we're going to make on top of this graph. Part A is the average velocity between time 1 and time 3. What is average velocity? Average velocity from t equals 1 to t equals 3. Average speed is distance traveled divided by time. Average velocity is better described as change in position divided by time. With this function, you could write it as f of 3 minus f of 1 divided by 3 minus 1. F of t is a function. It's giving us the y value. F of 3 is the y value when time is 3. That is this number right around here, somewhere close to 4. F of 1 is the second coordinate of this point right there, something slightly bigger than 2. F of 3 minus f of 1 is a positive number in this case. It's this distance right here on the graph. And 3 minus 1, the time elapsed, represents this distance right there. That's 3 minus 1, which is, of course, 2. This is, graphically speaking, a rise over a run. Rise over a run for this curve, but technically speaking, also for a line. The line segment connecting these 2 points right there. Rise is this distance, run is this distance. I can make a right triangle in here. This is a slope for that line. This is the slope of this line right there. Now, I could estimate the slope, and that might be worth doing here. Again, f of 3 looks like it's close to 3.8. f of 1 looks like it's close to 2.2. You might say this is approximately 3.8 minus 2.2 divided by 2. That'll be 1.6 divided by 2. That will be 0.8. If the units of time were, say, in seconds, and the units of y were, say, in centimeters, this would be in centimeters per second. It's a positive average of velocity. That's a positive slope for that line. That line segment between these 2 points in this graph is called a secant line. Let's go ahead and put that in here. That's the slope of that secant line. Right? And it's about 0.8. We want to compare that with some other things. Part B is the average velocity between t equals 5 and t equals 6. Let's go ahead and write that down symbolically. Average velocity from t equals 5 to t equals 6. It's a similar kind of formula. It's going to be f of 6 minus f of 5 divided by 6 minus 5. But this will be a negative quantity for this example because between time 5 and time 6, the position graph is going down the object is moving downward along the y-axis, upward is positive, downward is negative, that's a negative velocity. F of 6 is smaller than f of 5. The numerator of this fraction is negative. What is it? F of 6 looks to be around, well, let's just say close to maybe 3.1 there. Not sure how accurately I'm drawing this. And f of 5 looks to be close to, well, maybe the same as f of 3, close to 3.8. So this is approximately 3.1 minus 3.8 divided by 1. Negative 0.7 centimeters per second. The negative sign just indicates that the object is moving downward. The particle is moving downward. You could still use units, for example, of centimeters per second here. Graphically, it's the slope of this line segment right there. It's negative. Rise over run is negative. If you take the run to be from 5 to 6, the rise is negative because the function is going down. I'm not going to estimate the other values. I'm just going to think about them graphically. Part C, the instantaneous velocity at time 1. That's a new concept. Instantaneous velocity. I don't want to get into the details to fully explain this until a video or two from now when we talk about the derivative. This is the derivative of this function at time 1. Graphically, it's the slope of something called the tangent line. This thing's called a secant line. It connects 2 points in the curve. The tangent line, well, some people describe it as just touching the curve. That's actually not the best description unless your curve happens to be a circle, just touching the curve at one point. Because there's actually lots of little lines you could draw here that conceivably could touch the curve at one point, like a line like that. A better description of the tangent line at this point is it's the line that the curve looks most like as you zoom in closer and closer to the given point. Okay, this is called the tangent line at t equals 1. It is the line that the curve looks more and more like the closer you zoom in to that point when t equals 1. Okay, that's the best description, and even that's not perfect because it's still a little bit vague. Like, what does it mean to be the line the curve looks most like? You have to define rigorously what that means. Anyway, its slope is the instantaneous velocity at time 1. Instantaneous velocity at t equals 1. It is the number that we are talking about for part C. It is positive. Notice it's bigger than the slope of the secant line. Okay, so C is a bigger positive number than A. That's going to help us as we put these numbers in order. Part D, the instantaneous velocity at t equals 3. T equals 3 is right here. Its instantaneous velocity at that moment in time is the slope of that tangent line, which is about like that, which is still positive, but now smaller, closer to 0. So in terms of positive slopes here, the ordering would be this slope, then this slope, then this slope. Part E, we're doing the instantaneous velocity at t equals 5. That's the slope of this line, which is negative, and closer to 0 in slope than the slope of that line. And finally, F, the instantaneous velocity at t equals 6. That's the slope of this tangent line. These are tangent lines here that we're drawing. That's more negative than either of these. In fact, that's got to be the smallest value because it's the most negative. To actually now answer the question, yes, F is the most negative number. That's going to be the smallest. I'll write less than signs here. The other two velocities that are negative are the slope of that secant line and the slope of that tangent line. That one's the next most negative. That was the secant line that represents the average value between t equals 5 and t equals 6, the average velocity. So that is D. Oh, no, excuse me, that was B. A little confusing here. That was B right there. Then the slope of the tangent line there, that's the instantaneous velocity at t equals 5. that is E. Then we got positive slopes. The one closest to 0, the smallest one, is the slope of the tangent line at t equals 3. And that, you can see, is the instantaneous velocity at t equals 3 is d. Then we had the slope of the secant line right there. That was a, the very first thing we thought about, the average velocity between time 1 and time 3. And then finally, the biggest thing was the tangent line there, that slope, that instantaneous velocity at time 1, that is c. So this is the ordering down here that is the answer to the question. In number 3, we're back to east-west motion from home, but this time with a bike instead of a car, and we've got numerical data giving us the eastward distance from home as a function of time here. Starting from home, a person rides a bike straight east along a bike path before turning around at time t equals 2.5 hours and then coming straight back home. Okay, numerical data, we're not describing how the person rides, whether the person speeds up and then slows down, stays at a constant speed for a while, whatever. We're not describing that, other than to say that at time 2.5 hours, that's when the person turns around and comes straight back home. The table below gives the bike's distance in kilometers east from home. So this is not really a distance traveled, it's a position really, because it's a distance east from home as a function of time t in hours. Part A says find the average eastward velocity, sometimes could be negative, and average speed, can't be negative, of the bike over the interval from time 0 to time 0.5. Let's do that first. Average velocity from t equals 0 to t equals 0.5 is going to be, we are talking velocity here, so it's the change in d divided by the change in t. I'm using delta notation here. This little triangle, it represents the Greek letter delta. It means change in. So that you could write this in function notation if you like. I didn't give a name to this function. D could be equal to f of t, so f could be the name of the function. But sometimes we abuse notation and just use d for both the variable name and the function name. This is pretty common. It's technically not a good thing to do. It's called an abuse of notation, but we won't worry about it. D of 0.5 is 10. D of 0 is 0. 10 divided by 0.5 is 20. What are the units? We do have units in this problem, so the average velocity from time 0 to time 0.5, which would be half an hour, is 20 kilometers per hour. Does that mean you're going 20 kilometers per hour the entire time? Not necessarily, okay? In all likelihood, not. That's your average velocity. Graphically, if I drew a graph, which I won't bother doing, it would be the slope of a secant line. What about the average speed? That's going to be the same as the average velocity in this case, because we're moving in the positive direction. If we're moving in the negative direction toward the west, the average velocity would be negative. The average speed would be the absolute value of that. So we also get 20 kilometers per hour for that question. This is because the motion is to the east, which is the positive direction, the rightward direction. For part B, it says find the average eastward velocity and average speed of the bike over the interval from time 2.5 to time 4. 2.5, that's an important time. It matches that one. That's when the biker turns around and starts going to the west. Average velocity is still delta d over delta t. D of 4 minus d of 2.5 divided by 4 minus 2.5. But now that numerator is going to be negative. Graphically, this is the slope of a secant line. That will be a negative slope. D of 4 is 0. This is not total distance traveled. It's distance eastward from home, position. D of 2.5 is 30. 4 minus 2.5 is 1.5. So we have negative 30 over 1.5. 30 over 1.5 itself is 20. So this becomes negative 20 kilometers per hour. Okay? Happens that the absolute value of this is the same as the answer for part A, but that didn't have to happen. That's just a coincidence. What's the average speed? When I say average speed, I mean how fast are you going? It can't be negative. In this case, because now the motion is to the west, this is the absolute value of the average velocity. So that's back to 20 kilometers per hour. Okay? So you got to be careful. You got to think about direction. Part C, find the average eastward velocity of the bike over the entire interval from time 0 to time 4. And what does this tell you about the bike's movement? We already know what the bike's movement is about, but let's go ahead and write it anyway. The average velocity, in this case, delta d over delta t, is d of 4 minus d of 0 over 4 minus 0. Both d of 4 and d of 0 are 0. This is 0 minus 0 over 4, 0 kilometers per hour. Wait a minute, does that mean the bike didn't move? No, it did move. It went from east to west, starting from home, came back to where it started. What it means is the bike ended up back where it started. Okay? That's what it means. Ended where you started. The total average speed in this context, you got to be careful. I can't do what I did in either part A or part B here, because in part A, during the time interval from 0 to 0.5, I was always moving to the east. And in part B, the time interval from 2.5 to 4, I was always moving to the west. And that's what allowed me to do what I did in parts A and B. But in part C, if I were asked for the average speed, I purposely didn't put it in there, the answer would not be 0, would not be the average velocity, the absolute value of the average velocity. What you'd have to do to figure out the average speed is you'd have to think about the total distance traveled instead of just the distance eastward from home. And you'd end up with a function whose values when you move to the east are the same as this one, but as you continue and you're moving to the west, the values would keep increasing. It's kind of like the very first problem. Instead of a 15 there, you'd have a 30 plus 15 is 45. And instead of a 0 there, you'd have a 45 plus another 15 is 60. The average speed over the entire time interval would be 60 divided by 4, and that would be 15 kilometers per hour as an average speed over the entire time interval where you go back and forth. Our last problem is a symbolic problem. We're given a function with a formula s equals f of t equals negative t squared plus 4t that gives us the distance from a starting point. Distance from means position, not total distance traveled. This function over the time interval will have a graph that goes both up and down, increasing then decreasing. It is a quadratic function with a negative coefficient of t squared. Its graph will be a parabola that is concave down. This is t versus s. It is a little funny. S is used here not for speed but for distance from the starting point. That actually is fairly common, but S doesn't represent speed. It represents distance from starting point in this case. We're ultimately going to be, while finding some average and instantaneous velocities here, symbolically, we're also going to do a limit calculation at the end to confirm an instantaneous velocity. Limit calculations are about calculus and derivatives, so we're hinting at calculus and derivatives here. All right, part A, find and geometrically interpret the average velocity between t equals 1 and t equals 1 plus h if h is 2, h is 1, h is 0.1, h is 0.001. Sounds like a lot to do. Here's a way you can make your work faster. You can do it for a general h first, simplify it, and then plug in these different h values. So the average velocity from t equals 1 to t equals 1 plus h. Let's do it in the abstract first, and then we will plug in these different values of h. Instead of delta y over delta t, you would write delta s over delta t. And so instead of delta d like we did in the last problem. S is the dependent variable. This is change in position divided by change in time. This is f of 1 plus h minus f of 1 divided by 1 plus h minus 1. The bottom simplifies. The 1's cancel. and you're just left with an h. This is sometimes called a difference quotient in calculus, and we're ultimately going to take a limit of the difference quotient. But in this case, let's just simplify it for this function. This is tricky, okay? Lots of people have difficulty here. F is the name of the function. It's not a number. F of 1 plus h is not the same as f of 1 plus f of h, okay? It's not the same. You need to understand how to substitute an expression, even if it's a complicated expression, into a function. And the way you do that is you look at the function's formula, and wherever you see the independent variable, in this case t, here and here, you replace the t with whatever is inside the parentheses here. In this case, that's 1 plus h. So, being careful, looking here and here, comparing, I need to replace t with 1 plus h, so I'll get a negative 1 plus h quantity squared, that's replacing the t there with 1 plus h, plus 4 times the quantity 1 plus h, that's replacing the t here with 1 plus h. That expression is this entire thing, f of 1 plus h. Now subtract f of 1. F of 1, I get negative 1 squared. By the way, you'd square first and then do the negative sign. That's what that notation means. Plus 4 times 1, replacing the t with 1 in both spots. 1 squared is 1, negative of that is negative 1, plus 4 is 3. This is a 3 here. All divided by h. Now simplify. Expand this out. It's 1 plus h squared, meaning 1 plus h times 1 plus h. And then don't also forget about the negative sign in front here. But if I FOIL this, first times first, outside times outside, inside times inside, and last times last, I get 1 times 1 is 1. Outside times outside is h, inside times inside is h. H plus h is 2h. And then last times last is h times h is h squared. Don't make the mistake of forgetting to FOIL here. The answer is not 1 plus h squared. You need the extra plus 2h in there. Distribute the 4 through here. I get plus 4h. Then I'm subtracting 3. Distribute this minus sign through. Effectively, I'm multiplying all those terms by negative 1. 4 plus negative 1, or 4 minus 1, is 3, but 3 minus 3 is 0. Any term that doesn't involve an h goes away. Say that again. This negative becomes a negative 1 there. 4 plus negative 1, which is the same as 4 minus 1, is 3. Positive 3 minus 3 is 0. The constant terms cancel. What you're left with are terms that involve h. You've got a negative 2h there, plus 4h is 2h. And then you have a negative h squared, like that. This gets divided by h. This can simplify. When h is non-zero, I can divide out the h because I can first factor it out of the top, like this, and then divide it out to say this equals 2 minus h when h is not 0. Now we are ultimately going to think about what happens to this quantity as h goes to 0 in the limit. Kind of a subtle concept. Anyway, this is a very nice simplified formula for the average velocity. So how do we use it? Now for part A, we want to plug in different values of h. 2, 1, 0.1, and 0.001 into this. So part A, part 1, h is 2. I plug in 2 into this expression. I get, hey, 0. The average velocity is 2 minus 2 is 0. What in the world's going on there? In the picture, this actually is t equals 2 right here. 1 would be around here. 3 would be around here. I'm thinking about the average velocity from time 1 to time 3 here because I'm letting h equal 2. The function outputs here and here are the same. The slope of the secant line is 0. The average velocity during that time interval is 0. The object is moving, goes back and forth. From time 1 to time 3, you're back where you started, at time 1. When h equals 1, we get an average velocity of 2 minus 1 is 1. Slope of a secant line from here to here is going to be slope of 1. When h equals 0.1, the average velocity is 2 minus 0.1 is 1.9. And when h equals 0.001, the average velocity is 2 minus h, 2 minus 0.001, and that will be 1.999. And if we had units, these are velocities that are units of s per unit of t, maybe meters per second or something like that. Okay? Part B. Estimate the instantaneous velocity of the particle at time t equals 1. That's the slope of the tangent line. Should be pretty clear. These numbers are approaching 2. That should be the answer for part B. The instantaneous velocity at t equals 1 should be the limiting value of these numbers. These numbers are getting arbitrarily close to 2. This should be 2 meters per second or whatever. Is that really right? Or is it just a guess? Part C says do a limit calculation to confirm your answer to part B. What do I mean by limit calculation? I mean compute the limit as delta t goes to 0 of delta s over delta t. Delta t is h. That's the same as the limit as h goes to 0 of f of 1 plus h minus f of 1 divided by h. That's the limit as h goes to 0 of this thing right here. Instead of rewriting that all down, I'll just put an arrow here. You could pause the video and write it down again if you want. And through showing the same algebra steps that I did here, when I went to here, then here, then here, then here, I can keep carrying the limit sign along, do this exact same algebra with the limit sign being carried along, and in the end, get a limit. Well, let me show the last 2 steps. As h goes to 0 of this thing. And I claim that equals the limit as h goes to 0 of this thing, 2 minus h. And I claim that is 2 minus 0, which is 2. The most hand-wavy part of this really is in, maybe you might say, these last couple steps. Everything else is fine. This is the definition of the instantaneous velocity, also called the derivative of this function at time 1. This is perhaps the most fishy step there. I'm letting h approach 0. Lim h goes to 0 means h is getting closer and closer to 0 without actually equaling 0. How can I say these two limits are the same? Because these functions of h here and here are only equal when h is non-zero, because this one's undefined when h is 0, because you can't divide by 0. In the formal definition of a limit, if I'm letting h go to 0 here, I am letting it get closer and closer to 0 without actually equaling 0. I'm letting it get arbitrarily close to 0, you might say. Since these two expressions, these two functions of h, are equal when h is non-zero, and since I'm not literally letting h equal 0 when I think about this limit, until the end, confusingly, if this limit exists, then this one has to exist as well, and they have to be the same. Because these expressions here and here are the same when h is non-zero. And technically, in the definition of a limit, I actually don't care about what happens to the function when h equals 0. So that justifies this equality. But what about this equality, where I did end up plugging in h equals 0? The answer to why you can do that is this function here, as a function of h, is a continuous function. Its graph is, in fact, a straight line with a negative slope. You can draw it without picking up your writing utensil. And that one, it means it's a nice function. It means its limiting value, even though in the definition it doesn't matter what happens when h equals 0, because this is such a nice function, you can plug in 0 to find the limit. The function outputs do indeed get arbitrarily close to 2 as h gets sufficiently close to 0. And that's why the limit is 2. These two, if you graph these two functions, they both have the exact same graph as functions of h, except this one would have a point missing at h equals 0. Its graph would have a hole in it. And this one, 2 minus h, fills in the hole. It's called a removable discontinuity. They both have the same limiting value, though. Second coordinate of the missing point 2 for this function here. Okay? Very, very subtle concept, but very, very important for calculus and physics. Thanks for watching.